Okay, welcome to 3.1. 3.1 is max and min, okay? And the mantra we're going to live by in chapter 3 is, when in doubt, take the derivative, set it equal to 0. For most part, that's going to work. Now, before we get into this lesson, let's talk about what the difference between a local max and an absolute max is, okay? First of all, one thing you got to understand is absolute max and min can occur at endpoints. Locals cannot be at the endpoints. So when we're looking at this example, okay, here is a minimum value. It's lower than all the other values, and it's at an endpoint. Therefore, it has to be an absolute min. Whereas these 2 points here are local mins. Why? Because they don't occur at endpoints, and they're not the absolute lowest point. Look at the local min, local max, okay? Here we have nothing. Why? Only an absolute max can occur there. Why? It's an endpoint. You look here, that's not at the endpoint, but it's the absolute max. Why? Because it's the highest point. Here, you have a local max because it's not as high as the absolute max, and it's not at an endpoint. So when doing these, you want to keep in mind that local min and max cannot occur at endpoints. Absolute min and max can. So moving right along, let's take a look at this problem. Now this problem is difficult in that, first of all, it's a product rule with a square root function. So here's how you find the absolute min and absolute max. What you want to do is you want to take the derivative, set it equal to 0. That's going to identify the slopes at these points, okay? Wherever there is a hump, okay, take the derivative, set it equal to 0. Remember, that's the horizontal tangent line. That's what we're looking for. That'll give us our values for which we're going to plug in. So we're going to move on and do that. Now we have the product rule here. So again, when we do f prime, what you want to do is write the first times derivative of the second. Now remember, this is 4 minus x squared to the 1/2 power. So when we do that, it's going to be x times 4 minus x squared to the 1/2 derivative. So it's going to be derivative of the inside, which is negative 2x times derivative of the outside. Rewrite to the negative 1/2 power, okay? Then what we're going to do is take that and multiply times the derivative of the first times the second. So that's going to be square root of 4 minus x squared, okay? Now we have to simplify this. Well, I'm going to do all the hard work for you and tell you that this simplifies to the following function. 4 minus 2x squared over square root of 4 minus x squared, okay? Now, there are your two values. Now, the thing with this is you're going to have to, when it's a rational function, you're going to have to set the numerator equal to 0 and the denominator equal to 0. Just remember our sign analysis rules hold true here as well. So what you're going to do is you're going to take 4 minus 2x squared equal to 0, all right? So you're going to end up with 2x squared equals 4, x squared equals 2, x is plus or minus 2. Now, they give us an interval, and that's going to come into play in a minute. But before we do that, realize, is negative 2 in that interval? It is not. So we automatically eliminate negative 2, so the answer is just 2. All right, that's always something you want to check for. That happens a lot. You're going to get something outside that interval. You want to make sure that you're talking about those points. Now we're going to set the bottom equal to 0. So we're going to say 4 minus x squared equals 0. So you're going to get x squared equals 4. So x equals plus or minus 2. And again, oh, I'm sorry, this is plus or minus square root of 2 over here. Sorry. So this is plus or minus 2. Again, negative 2 not in that interval, so it's just 2. So we have square root of 2 and 2. Those are possible local or absolute maxes. We also have to check these 2 points, the endpoints, if they don't match one of these. Now, 2 is there, we have 2 there, so we're good. So we're going to have to check negative 1, square root of 2, and 2. And how do we check that? Well, we're going to go back to the position function, the original function. We're going to plug in those values and see which one's the highest y value, which one's the lowest. All right, so we're going to take f of negative 1, this endpoint. We're going to take f of square root of 2, and we're going to take f of 2. We're going to plug it into the original function here. go ahead and pause the video and see if you can do that. Okay, welcome back. When you do that, you're going to get f of negative 1 is negative square root of 3. F of square root of 2 is 2. And f of 2 is 0. So, what does that mean? Well, we're only looking for absolute maxes. So we want the highest and the lowest points. This is definitely the lowest because it's negative, and this is definitely the highest because it's bigger than 0. So here's how you write your absolute mins and maxes. You write absolute max equals 2 at x equals square root of 2. Right there. Boom. Absolute min equals negative square root of 3 at x equals negative 1. Okay? So that's how you find absolute min and max. All right? Moving on to the next slide. All right, so now it says a function f has local at c if when x is near c, an open interval containing c, f of c is greater than f of x. A function has a local min if f of c is near c, and you have f of c is less than or equal f of x. All right? So, when you're doing this problem, when you're doing these, you're going to have a local min is going to be lower than the function itself, like here and here for local mins, whereas f of c highest points are right there. Okay? So that's what we're going to be looking at. All right, now, we're going to find the extreme values of f of x 0 to 5 of this function. Now, this is a much easier function, but we're going to find all the extreme values, meaning we're going to find all the local, all the absolute, and maxes and mins. All right, so when in doubt, take the derivative, set it equal to 0 here. So you're going to get f prime of x is equal to 3x squared minus 18x plus 24. Okay, so we're going to go ahead and set that equal to 0. And you're going to get factor out of 3. You're going to get x squared minus 6x plus 8. Set equal to 0. Factor that trinomial. You're going to get x minus 4, x minus 2. So x equals 4, x equals 2. Now again, we're on an interval from 0 to 5. 4 and 2 both fall inside that. So now we have to check them all. So we're going to start with 0. Then we're going to go 2, 4, and 5. So we're going to go ahead and do f of 0, f of 2, f of 4, f of 5. Go ahead and see what you get there. Pause the video. Okay, welcome back. We got the following values. Negative 10, 10, 4, and 9. Okay? So, that'll tell us where our absolute max is, okay? Absolute max. Now, when we do our local min and max, we're going to use sign analysis. So we're going to go ahead and put on here, okay? Now we know 0 and 5 are endpoints, can only be absolute mins and maxes. Whereas 2 and 4 are going to be our places that we want to check. Now, again, when doing this function, you want to plug it into f prime, because that's going to tell us the slopes. So this is going to be of f prime. All right, so we want to make sure we're plugging into f prime. So we're plugging in here. So we're going to plug in our sign analysis. So pause the video, see what you get there. Okay, welcome back. You should get positive, negative, positive. Now, when you do that, positive on f prime tells me what? Positive slope. Negative tells me negative. Positive tells me positive. So now you can see this would be like a hump. And that hump would look like this. Okay? And then this one would be a hump, but it would look like that. See? So you can see right here and here, you have a local max at 2, a local min at 4. Okay? So that's how you know what these values are. So we've now identified some key points on this graph. What have we identified? from here, we know that the absolute max is 10, and it's at x equals 2. We know the absolute min is negative 10, and that's when x is 0. All right? Then, over here, we have 2 is also a local max. Okay? 2 is also a local max. Why? Because, again, if it occurs off an endpoint, it could be a local max if there is no other local max. Okay? And then 4 is a local min because you get 4. Okay? I'm sorry, that's 6. I don't know why I wrote 4 there. That is 6. Sorry. Hopefully you fixed that. All right, so now let's write down what we got. So we got an absolute max. All right, that is equal to 10 at x equals 2. We got an absolute min, okay, equals negative 10 at x equals 0. And then from over here, we get a local max of 10 when x equals 2. And we have a local min, all right, a local min of 6 when x equals 4. Okay? So that should be a 6 there. It's my fault. Okay? All right, so that's how we're going to do it. We're going to use the sign analysis chart to do local min and max. We're going to do plugins to find our absolute min and max. All right? Any questions there? All right, moving on. All right, so now we're going to do find the local extrema of g of x equals square root of x, or I mean the absolute value of x. Now, let's watch. Remember, absolute value of x equals x if x is greater than 0, negative x if x is less than or equal to 0. And what does that graph look like? Okay? That graph is there. So, what do we know? Well, if you take the derivative, okay, we know that on this side it's negative, on this side it's positive. So there is no local max, okay, no local max. They didn't give us an interval, so there's no endpoints. So there is no local max. Here would be a local min, but remember, what about a corner? Do you remember? F is a corner, so f prime does not exist at a corner, okay? So, cannot find local extrema of that. All right, now, extreme value theorem says if f is continuous on a closed interval and f attains an absolute maximum value and an absolute min at some numbers c and d on interval a to b. So what you have here, people, is you have closed continuous on a closed interval from a to b. That's here. Okay, the two endpoints closed brackets. Remember. Then it says f has an absolute max and an absolute min somewhere in between them. Okay, at some numbers c and d on a and b. So here's some different examples. All right. Functions that violate the continuity condition on a closed interval may not have a max or min on that interval. Okay. These are discontinuous graphs, so this may not have all that, as well as this continuous function. This is an open interval here, okay, not a closed interval. So you have to have a closed interval, you have to have continuity. All right. Now we're going to get to Fermat's theorem, or Fermat, I guess we would say. If f has a local max or min at c, then if f prime exists, then f prime of c equals 0. Okay, so f prime of c does not guarantee a local min or max, all right? So the critical number c is the value such that f prime of c equals 0, or f prime of c does not exist. Note the min or max is f of c, and it occurs at x is c. That is the definition of Fermat's theorem, okay? So, we're going to hold off on that. I haven't seen that on the final. I'm just going over. It's in the book. All right. So that ends the notes for 3.1.